Mm, are the slides on?
Yes, yeah, the
Yes.
slides are on.
Okay. Good morning, everyone. I am Joshua C. Agar from the Institute of Civil Engineering. With my co-authors, Dr. Jaime Y. Hernandez Jr. and Assistant Professor Timothy John Acosta, I'll be presenting to you about Typhoon Roll. So, uh, wait a minute. The presentation with this outline tackles the question how strong Typhoon Rolly is. So to brief you about Typhoon Rolly, by the time it made landfall on November 1, some people already regarded Typhoon Rolly as the strongest landfalling tropical cyclone, supposedly supplanting Typhoon Yolanda's record in 2013, with the Joint Typhoon Warning Center estimating 1 minute sustained winds of 315 kilometers per hour. On the other hand, Pag-asa estimated that the 10-minute sustained winds of Typhoon Rolly was less than that of Yolanda, which is at 225 kilometers per hour. So even so, at such strength, public storm signal number 5 was raised for the first time in the Bicol region, at Catanduan specifically. The damage across the province was extensive, and even the Doppler radar image released by Pag-asa, here shown in the right, uh, tells a picture of how strong it is. The reason is that it was obtained from the ET radar station instead of the much closer Virac radar station, which suffered extensive damage, with the radome being blown off. The radar station has once survived the peak winds of 320 kilometers per hour brought by Typhoon Remin, which is a record for the whole Philippines. The province has also experienced the strongest typhoons in the past, like Typhoon Sining in 1970 and Typhoon Rosing in 1995, and more recent typhoons like Nina in 2016 and 2019. But the damage brought by Rolly was never seen before. So as a researcher who tackled researches on typhoon, previous researches, and its effects on structures, I began to search for the answers along with my co-authors on how strong typhoon roll is. For evaluating the wind hazard is vital in estimating the extent of the wind risk of such typhoon to the communities affected, which is also part of the disaster risk management and assessment initiatives. This research has adopted the framework that was pictured on the background in the previous slide. It's mainly divided into two, the forensic structural analysis and the forensic meteorological analysis. As typhoons were regions of low pressure, just like what the Jesuits did in the 1800s in the Manila Observatory, the pressure drop was recorded across weather stations of Pag-asa near the path of Typhoon Rolly as it made landfall. Knowing the storm track of Typhoon Rolly, we can establish the distance of the stations from the storm center. That gives us the relationship between the pressure and the distance. And fitting the hyperbolic model yields us the minimum central pressure of the storm at the center, which is what 905.37 hectopascals. The need to obtain the pressure field arises from the need to evaluate the pressure gradient, which was one of the main forces behind the primary circulation of a tropical cyclone, apart from the Coriolis force and the centrifugal force. Substituting the hyperbolic model to the equation in the previous slide, which is the cyclotropic balance equation, enables us to evaluate the wind field of Typhoon Rolly, on which the maximum winds were evaluated to be at 229.6 kilometers per hour. However, comparing the model data points to the actual data points would bring us to question why actual wind speeds were lower than the wind speeds of the model. The answer of that is a concept called wind exposure. It's a factor covering direction of winds, effects of topography, the position of the storm with respect to the areas affected. To explain that briefly, we look back into history. We name some notable typhoons in the past, like Typhoon Sisang, where it directly hit Legazpi City, and Typhoon Riming in 2006, where it hit Catanduanes, and from the near present, like Typhoon Nina and Typhoon Tisoy. All of these storms traverse across Laguna Gulf, which is the body of water between Catanduanes and Albay. Uh, Typhoon Sisang, the difference was that Typhoon Sisang and Typhoon Tisoy moved closer to Albay, whilst Typhoon Rolly, Typhoon Nina and Typhoon Reming moved closer to Catanduanes, and I was assessing Typhoon Rolly was assessed to be similar to that of Typhoon Nina in terms of proximity and similar to Typhoon Reming in terms of intensity. With the modeling being done, we evaluate the gas factors, which were then used to project the wind speeds brought by Typhoon Rolly. Doing the same evaluation on Typhoon Nina, Rolly was projected to have brought a peak gust of 275 kilometers per hour at Virac. On the other hand, the World Meteorological Organization's recommendations on gas factors suggested that the peak gas may be at around 312 kilometers per hour. Replicating the exposure scenario on Reming, on the other hand, on the radar station, leads us into estimating the peak gas experience by that radar station to a staggering 378 kilometers per hour. It's important to note that the scenarios that were mentioned were projections alone, but that's where the forensic structural analysis comes at hand. With the new normal, of course, we can't do field surveys since researchers weren't permitted to do such field surveys. Thankfully, there were social media. People have posted what they have witnessed during the onset of Typhoon Rolly, like this school building, for example, in Catanduanes, where the entire roof system was blown away. To simulate the wind flow around the school building, a CFD analysis was performed. In turn, the aerodynamic load experienced by the structure is obtained. Structural analysis was also performed to replicate the scenario captured on footage. Using the capacities evaluated by the past researchers like Dugiles and Tan in 2016 and 2017 respectively on hook rebars, which holds the group system in place, Monte Carlo simulation was then performed to establish the probability of the event captured on footage from happening based on various scenarios. So we have a statistical distribution of capacities, so we perform Monte Carlo simulation, exploring the possibilities on or capturing the statistical distribution of those capacities mentioned. Same goes with the second case at Catanduanes National High School, where two spans of roof framing suffered extensive damage. However, in this case, we can't ascertain the direction of the winds since there was no footage documenting the failure from happening. So the CFD analysis was performed on different angles of approach in the hallway of the school building facing northeast. So it is facing to the northeast here. So we then evaluate the aerodynamic loads, which were then transmitted to the fasteners, which were then transmitted to the purlins, which were checked whether they exceeded their respective bending capacities. The figure on the left shows the spans being subjected to the analysis, span 1 and span 2. The figure on the right shows the relationship between the damaged states of the purlins and the wind speeds. This is for the first span, and this is for the second span. The lower bound wind speed is established where all the purlins on the leeward side and experienced failure, and the subsequent damage of the other sections were propagated damages. Whilst the outward bound wind is established at scenarios where all purlins at the leeward side of both spans experience bending failure on the onset. This is for 15 degrees, which has a lower bound of 70 meters per second and upper bound being 81 meters per second. This is for 30 degrees from 63 meters per second to 71 meters per second. This is for 45 degrees from 61 meters per second to 72 meters per second. 60 degrees from 69 meters per second to 74 meters per second. 75 degrees, 71 meters per second to 80 meters per second. To summarize, the results of the tropical cyclone modeling agrees more with the estimates of Pagasa, who estimated that the maximum wind speeds were at 225 kilometers per hour. The range of the estimates from forensic analysis also agrees with the tropical cyclone modeling and some key projections. However, it is important to note that these were still projections. To validate the result, the data from Virac station is needed. So we would be asking Pagasa, which is our partner in one of our research projects, how strong the winds that Virac station experienced. But on the other hand, we must express solidarity for the Bicolanos, especially in Catanduanes, who are affected by the storm. Bangon Catanduanes. Thank you very much. That is my presentation.
Thank you very much, Joshua, for that very informative and insightful presentation. And now we open the floor for 1 to 2 questions. From Sheila, from your forensic hazard assessment, how will this be of help to our local DRRM councils or offices in assessing hazards in future typhoons, hopefully lessening damage to lives and property?
To answer that question, let me give you a details about our research research project, which in collaboration with Pagasa and eBooks, which was discussed perhaps by Dr. Paringit earlier, which evaluates yung wind risk. So part po ito ng, though offshoot na topic po ito, part po ito ng parang i-collaborate po namin with Pag-asa yung aming findings. Then in turn, we will produce a severe wind assessment for the whole Philippines.
Okay, maybe last question from Sir Andres Winston Oreta. How can the study be used to improve the wind design?
Supposedly nakapag-establish na po tayo ng extreme value parang this will help us in establishing extreme value functions in updating yung ating design wind speed. So in turn, halimbawa mag-update ng ating 100-year winds, i-adjust natin with the new data coming from Typhoon roll.
Okay. We still have a number of questions. I think we can ask them to forward it to you as in chat, Josh.